talk about conservation of momentum. We're going to learn how to describe momentum of a system, would be conserved, discern if momentum is conserved or not, use momentum diagram or vector diagrams, and calculate some mission measurements. Here we go. The law of conservation of momentum. This is like one of the pillars of classical physics. The total momentum of a system is conserved if there are no unbalanced external forces acting on objects in the system. The total momentum of the system is conserved if there are no unbalanced external forces acting on objects in the system. Total momentum of the system is conserved if there are no unbalanced external forces acting on objects in the system. If there are no unbalanced external forces in the system. Okay, there's a lot of new terms in there that we don't know, and we will unpack. But the first thing I want to bring your attention to is this the same condition for which mechanical energy is conserved? Mechanical energy is conserved when or if, same thing as that, or different? If there's no non-conservative forces doing work. Is that the same thing here? It is not. Okay, so do not take what you learned about like, oh, is it conserved or not? This is a completely different ball game. Completely different condition. Okay. And we're going to learn what this means momentarily. Okay. So the first thing that might seem weird is what's the system what you speak of? Okay. A lot of words here. I'm just going to verbalize it. The system is a way to highlight what objects do we care about. It's just to say, hey, I want to focus on these objects here. So I'm going to isolate them. I'm just going to look at those things that we're going to put those objects that we care about in the system. Okay. You can put as few as one object in the system. You could put in a lot of like many objects in the system. You could put the whole universe in the system if you really, really wanted to. Probably wouldn't be beneficial, but it's just a way to like, hey, I'm focusing on these objects. Okay. All right. Have this scenario. You have a bowling ball rolling and hits a bowling pin. Okay. On the moment of impact, I want you to draw the free body diagram of the ball and the free body diagram of the pin. We're going to ignore air resistance. We're going to ignore friction. So during the moment of impact, How'd we do? Okay. I'm going to call the force from the impact applied force rather than normal force. I mean, you could argue that it's normal force. I'm going to say applied force just to make a distinction between these two and not to get them confused as we're talking about them. Okay. So good with that? Okay. Now, if you're following along on the slides, I'm going to go through these next 3 slides just verbally. Okay. So let's say that we just put the pin in the system. So sometimes some textbooks illustrate that by drawing a dashed line around the object and focus. Okay, so that's our system. Let's look at each of these forces acting on the object in our system. Normal force. What object caused that or created that? Like, where did that normal force come from? What is it? What? Yep, from the floor, the ground, the bowling lane, whatever you want to say. Is the floor, the ground, part of the system? Nope, just the bowling pin. So we're going to say that the normal force is an external force. It's coming from an object outside the system. Okay. Applied force. What object caused or created that? Bowling ball. Is the bowling ball inside or outside the system? Outside the system. So this applied force would be also considered an external force. It is from an object outside the system. Force of gravity. What object caused or created that? Remember the raindrop? The earth. Okay. Is the earth inside or outside the system? Outside the system. So this too is an external force. So like, oh my goodness, we don't have any, like, it's all external forces. Like, oh, okay. However, what happens? What does normal force do to the force of gravity? It cancels it out. It balances it. These two forces, though they are external, are balanced. But is anything balancing this external force? No. So, are there any unbalanced forces acting on an object in the system? Yes. So is momentum conserved? Not conserved. Everybody see the questions I'm asking? Okay. Now, how does that play out in real life? How much did the pin have momentum before the collision? Did the bowling pin have momentum before the collision? No. Did it have momentum after the collision? Yeah, probably. Yes. Okay. So did the pin's momentum stay the same? No. So it was not conserved. Does that make sense? Tracking so far? Okay. Now, what would happen if instead of just saying the pin is the system, I say, well, I want to put the ball in the system as well. So both the ball and the pin now are considered in the system. We're going to go through the same series of questions. Okay, and we're going to say, oh, normal force is from the ground, it's an external force. Force of gravity, that's from the earth, so that's outside the system. That's also an external force. Oh, those two forces cancel each other out. Okay. This force, where is that one from? from the pin, right? Is the pin part of the system? Is that an object inside the system? Yes. Therefore, this is an internal force. And we're okay with internal forces. Well, what about this guy? What object is creating that one? The ball. Is that inside the system? Yes. So, are there, in this scenario, with the ball and the pin, are there any unbalanced external forces acting on objects in the system? No. So is momentum conserved for the system? Yes. We're seeing the train of questions that I'm asking myself. Okay. So how this is played out in life, what has this demonstrated? So initially, before the collision, did the ball have momentum? Yes. Did the pin have momentum? No. So the total momentum of the system beforehand is just equal to how much momentum the ball had originally. After the collision, both are moving, but the total momentum of the system will still be equal to how much momentum the ball had initially. The total momentum of the system is still conserved, even though both things are moving. Okay, so that's kind of how that fleshes out. So some people, not many, but some people are like, well, why is it conserved like that? That's just a rule that you just made up. Like, why is that valid? Something that, okay. Which object, the ball or the pin, is experiencing a greater force? Pin? The same? The same because Newton's third law. Okay? So both the ball and the pin are experiencing the same force. These two forces are Newton's third law. Which object experiences that force for a greater period of time? Do you remember the collision carts that like crashed together and the spikes on the board that were like, okay? They experienced the same force, the same amount of force for the same period of time. Every time. The ball can't touch the pin longer than the pin can touch the ball. Does that make sense? They're in contact with each other for the identical amount of time. So they both experience the same amount of force for the same amount of time. Therefore, they both experience the same change in momentum. Everybody okay with that? Okay. But there is a important detail. The force causing that change in momentum on the pin was going to the right. So if we make to the right positive, it had a positive change in momentum. The ball experienced a force to the left that caused the change in its momentum. So it had a negative change in momentum. And this is why that the total momentum of the system stays the same, because the positive change of momentum of the pin is equal to the negative change momentum of the ball. You can see you are duly impressed. We're going to see how well it's stuck. Tell your neighbor. Correct answer is yes. You have gravity and normal force. They're two external forces, but they're balancing each other out. Good? This slides along at a constant velocity. Next scenario. Tell your neighbor. See him. See him. Correct answer is B. No. But let's say we include both players in the system. Correct answer now is yes. This is just like the bowling ball, bowling pin example. You okay with that? Next scenario. Tell your neighbor. Tell them why or why not. Correct answer is B. No. What's the unbalanced external force? Friction. Next scenario. Tell your neighbor. Tell them why you think so. Correct answer is I would say yes if you took your stick and you slid it across the ice and it hit the puck. but that's usually not what you do with hockey sticks. Okay? You're going to be swinging, exerting applied force on the stick. The hockey player itself was not part of the system. So, no, momentum is not conserved. However, if you included the hockey player in the system, and the stick, and the puck, would momentum be conserved? Yes. You all right with that? Okay. So watch yourself. I mean, do you see the magic of like, oh, we can make momentum conserved? You just have to stick in whatever exerting a force in the system. Okay. Tell your neighbor. Correct answer is no. Is mechanical energy conserved? Yes. But momentum is not. So I just wanted to highlight the difference here. But let's say we included the Earth as part of the system now. Would momentum be conserved? If we included the Earth in the system, then gravity then now is an internal force. Okay. Now, conceptually, this is true. But practically speaking, if you're trying to solve a problem and you're trying to use conservation of momentum, and you find that you need to include the Earth in the system in order to make momentum conserved, abort. Like, that is not a good way to solve that problem. There are other ways using physics to solve what you're trying to solve. Okay? We're not going to try to find the speed of the Earth accelerating up to the puck. See how ridiculous that is? Okay? Conceptually, it's valid, but at a practical standpoint, you're just dumb. Okay? All right. Does momentum have direction? Is momentum a vector? Does direction matter? Absolutely. So when we say that the total momentum of the system is conserved, that implies not only magnitude, but also the direction of momentum is also conserved. It stays the same. What do I mean by that? Let me kind of demonstrate it with this example. Is everybody okay with A to the right? The direction of the total momentum of the system is wrapped up just in the bowling ball, and the bowling ball is rolling to the right. Therefore, the total momentum of the system is also to the right. Okay. So the follow-up question to that is, what is the direction of the total momentum of the system after the collision? Well, I don't know. I mean, the pin's probably going to go that way. The ball, okay. We've discerned through this conversation, this long conversation, that in this interaction, if you put the ball and the pin in the system, the momentum is conserved. So the total momentum of the system beforehand is to the right. Afterwards, it still has to be to the right, because momentum is conserved both in magnitude and in direction. And that is an important detail. Get with that? That's a big difference between conservation of mechanical energy that did not have direction and momentum, which does have direction. Give this one a shot. Thumbs up when you have a guess. Thumbs up if you have a pulse. It's a rough day for some of you. Dr. Neighbor.
Yeah, I agree.
Correct answer is A. Agreed. Okay. Do you remember the energy bar charts? Okay. Those were tools. That was a tool to help us understand what was happening to the energy. It was like energy accounting. Okay. This next slide is a tool to help us understand what is happening to momentum. Okay. These are momentum vector diagrams. Okay. So I'm just going to demonstrate how this works with this example. So we had, the ball had 20 kilogram meter per second to the right initially. The pin had no momentum initially. We put both objects in our system, so the total momentum of the system is the ball's momentum plus the pin's momentum, and that equals 20 kilograms meter per second to the right. That's the total momentum of the system before the collision. Through our conversation, we discerned that the momentum of the system of the ball and pin is conserved. So afterwards, that system still has 20 kilograms meters per second to the right. Well, from the scenario, we said that the ball had 15 kilogram meter per second to the right. So 15 to the right plus something gives us 20 to the right. What is that something? 5 to the right. Okay, You might be thinking, that's stupid. That's a lot of work for something that I could do just thinking about it. Yes, that is true. However, I started you out with a very easy question. All objects here in this scenario are moving the same direction. It gets a little more complicated when things are moving in different directions. Tell your neighbor. And you guys' mental telepathy skills are impressive. It's just, correct answer is okay. Well, let's do this then. So we had 140 kilogram meter per second to the right. We had 200 kilogram meter per second to the left. I'm going to put both objects in my system. So that plus that is equal to 60 to the left. For ignoring friction, that collision is momentum conserved. Yes. So the total momentum of the system is still 60 to the left. Good with that? Okay. We'll revisit this football scenario next lesson. All right. What I have, skateboard, medicine ball, and me. Okay. I'm going to put, actually, this would not be beneficial if someone just came walking in. Okay. So I'm going to put the skateboard, me, and the medicine ball in the system. Okay. What is the total momentum of the system right now? 0. Okay. I'm going to throw this medicine ball as hard as I can that way. Okay. We know what's going to happen to the medicine ball. I want you to watch what happens to me. And also pretend that there's no friction. Which there is, but we're going to pretend there's not. Okay. Oh, and here's a cool thing. Sorry, timeout. This is so anticlimactic. Here's a cool thing about this unit. Vectors, yes. but the vectors are only going to be in one dimension. Right, left, up, down. They are not going to be at an angle. So you won't have to do components in this unit. You're welcome. I could, but we'll just, okay? So when I say, is momentum conserved, I'm just going to, for this example, let's just look at the horizontal direction, okay? And before the ball hits the ground, okay? So I'm throwing the ball as hard as I can this way. Ready, set, go. Okay. If there wasn't any friction, what would I do? I would keep on moving. Okay. So evaluate. I can answer that question. Have a conversation out loud with words. Was momentum conserved? It was? Wait a minute. Initially, how much momentum did I have? None. Afterwards, did the ball have momentum? Did I have momentum? How can you say it's conserved? It started with nothing, and now there's something and something. Why does it cancel each other out? They're going in opposite directions. Okay. Why also? Because they experience the same force for the same amount of time. B and C are correct, so D. How do we do? Okay. So if I was doing this momentum diagram, starts with zero, this starts with zero, the total momentum of the system is zero. Total momentum of the system afterwards is still zero. I'm making these numbers up completely out of thin air. 127. Again, I just made that up. This has to have 127. Okay. This plus this gives me that. Good there? Next question. Tell your neighbor. What do you say? Correct answer is B. I agree. Momentum vectors. These aren't really isolated at the beginning. We're just going to say 40,000 up. That internal explosion is an internal force. $40 going up. So if you have 50 going up, 50 up plus something is equal to 40 up. That has to be equal to 10 down. Wow, that's crazy. You have more momentum than what you started with. No, you don't. Magnitude-wise, yes, but you can't just look at magnitude. There's a direction aspect. The total momentum of the system is still 40 up. Okay, good with that. Okay, this last question, I would highly recommend doing a momentum vector diagram. And we're just looking in the horizontal direction. Have a conversation. Everybody have a vote? If you didn't do a momentum vector diagram, I'm pretty confident you missed it. One to the right, 0. Total momentum of the system, 1 to the right. Total momentum of the system is conserved. Put both the ball and the bowling ball, the golf ball and bowling ball in the system. Afterwards, the golf ball is bouncing backwards. How much? It really doesn't matter. Not more than 1. Everybody okay with that? Making this up. Let's say it's 0.7. Made that up. It's less than 1. 0.7 to the left plus something has to equal 1 to the right. What is that something? 1.7 to the right. What? It has more momentum than the golf ball did originally? Yeah, but the total momentum of the system is 1. Wow, does that mean the bowling ball is rolling faster than the golf ball? Remember, this is momentum, not velocity. Okay, the total momentum of the system has to be to the right. Therefore, if you have things moving in opposite directions, the thing moving to the right has to have more momentum than the thing moving to the left, because the total momentum of the system is still to the right. Get with that? Got a worksheet due on Monday. You're welcome. I love you so much.